So in our remaining time, I'm going to show you how to apply the Java Executor interface, that simple API, to a fun application called the PrimeChecker app. You will see this over and over again because we use it as a running example. And I'll explain first what the app does, and then I'll show you how you can use the Executor interface to implement it. So this app basically is a way to show how to use different features in the Java Executor framework, starting with the simple ones, to check if n random numbers are prime. So you click this button, and it generates a bunch of random numbers that are very large, and it checks to see if any of them are prime, and if they are, it says they're prime. If not, it gives you the smallest factor for the number. I think you probably know what a prime number is, but in case you forgot from 5th grade or whenever you learned about it, a prime number is a number it's a natural number that's divisible only by 1 and itself. So evenly divisible in the sense that you don't have any remainder. So here's the first 25 prime numbers, and of course, they don't get interesting until they get big. In this app, you can select n, where n is the number of prime numbers you want to check. You can start running the app, and there's certain interesting properties about this app. One is it's a great example of embarrassingly parallel processing, because computing random numbers and checking if they're primes, there are no dependencies whatsoever between any of the numbers. You can run them all in parallel, like doing your laundry, where you don't have any dependencies. Although, of course, you should wash your clothes before you dry them. But when you wash your clothes, you can run them all in parallel. You don't have to stop the loads and then rearrange them typically, as long as you don't overload them. This is also what's called a compute-bound task. Checking whether a number is prime just depends on how fast that computation runs depends on how fast your CPU is. So the faster the CPU, the faster it'll figure out whether it's prime or not. But there's no I/O, there's no blocking on locks. It's just cranking away and getting the results. The particular example that we use here is a brute force algorithm to check whether a number is prime, and I do that on purpose, as I'll talk about in a second. It's kind of like the Hulk, it's brute force. So as you can see, what we're going to do here is we're going to start, first of all, if a number can only be prime if it's greater than 3. We're only going to bother checking to see if a number is prime if it's greater than 3. Otherwise, we know it's prime. And you can see we start with the factor being 2, and we keep going while the factor is less than n over 2. And every time through this thing, we divide n by the factor, and then we multiply by the factor. And if we end up with n, then we know it was divisible evenly. And we crank away on this until we get up to n over 2, at which point we fall out and return 0. There are, first of all, notice this is a compute-bound algorithm. Return 0 if the number is prime, or its smallest prime factor if it's not, or smallest factor if it's not. And intentionally, it's meant to be inefficient. There are much more efficient ways to do this, and we'll look at some of them later, but this is a simple-minded way to do things. You can use the sieve of Arachnios, or whatever it's called, to do this as well. Here's how we actually run this in our program. In our app, we start by making a fixed size thread pool using the new fixed thread pool factor method. We are going to have the number of threads in that pool be equivalent to the number of processor cores that the Java execution environment thinks we have. So if you have an n-core machine, this will return n. We use this value since isPrime is a compute-bound task, as we just saw, so we want n to be the number of cores in this case, because there's no point in making it more. We could make it less, so we wouldn't end up using all the CPUs, but in this case, we're trying to crank away and maximize the CPUs. We have a user interface thread that generates random numbers, large random numbers that are then processed in the background by the thread pool. And internally, there's an unbounded queue that's used to queue up the work. So if you have 1,000 numbers you want to generate, but only 4 core, then you'll have a big queue to hold all the numbers you want to check for their primality, and only 4 of them will be running at a time. So here's what this thing's going to look like. We're going to have a little program that looks like this. We're going to generate a bunch of random numbers in the range S max value minus count to S max value. And the reason for doing this is we want to generate a bunch of duplicates. But we want these to be large numbers that have duplicates. Smax value is set to a large number like 1 billion. So we get large numbers, but there will be duplicates in them because we're going to subtract this and put them only in that range. And then each of these random numbers is queued for execution by a thread in the thread pool. And we do this by going through every one of the random numbers. And for each random number, we're going to execute this call, which is the PrimeRunnable call, or PrimeRunnable object. And we give it this, which is the activity for GUI display. Don't worry about that. And the random number itself. And then that's going to go ahead and run in the background. Here's what PrimeRunnable looks like. It implements runnable. So it's got a run hook method. Its constructor stashes away the activity and the candidate that we're checking to see if it's prime, the prime candidate. Here's the isPrime method. We just looked at that. That's the one that checks to see if the number's prime. And then here's the run hook method. This is the one that's going to be called in the background thread. And as you can see, it's going to check to see if the number's prime. And it'll return 0 or greater than 0 if it's not prime on the prime candidate. So that'll be running in the background in a pool in the thread, a thread in the pool. Although there's lots of these prime number instances, they will be running on a much smaller number of threads. So we might have gazillions of these, but a very small number of those, which is exactly the point. When the user clicks start computation, which is what happens when they click the button on the GUI, that's what starts everything running. Okay, so that's basically a quick overview of that example. When we come back on Wednesday, we will look at the evaluation of this thing. We'll cover other aspects of the program, of the executor framework, and we'll have the quiz.